So, as I promised, I am back. Today I want to talk a little bit about the NIST standard, okay, the international standard that is used to define all of the terms and constants in theoretical physics. So today I want to show you some of the tools that I use to investigate the parameters from the standard, the constants from the standard, and this is the tool right here. So I will make sure to leave a link to this in the description, but there is a website, so if you type in NIST code data, CODATA, you will find it right away. But I will make sure I leave the link to this. This is the tool that I use to search the database of all the constants, and when I am crunching my numbers in my computer program, I can look them up in this tool right here. Okay, there's also an ASCII searchable text page. This is hugely convenient. It's this right here. It's very convenient if I want to just look up numerical values. If I do some crunching in my computer program and I come up with a number and I want to see if this appears in the NIST standard, then I can look it up in here. So if I discover a parameter that is in the order of, say, e to the minus 25, I can do a search for that. Okay, and I can find all the parameters with that exact value, and so I can search the values, although the way they show them in this ASCII table, they have spaces in here, so you have to take that into consideration. Usually I just look for the first few digits and then I can find the rest of the numbers. So this is super handy, and also this one here where you can actually search the database. So I could type in, say, maybe I want to look up Planck's constant. Okay, and then there's all the different variations on it, and so I can click on this one and I can see I can get the value of the Planck's constant, and I can get the units. I can get the units that the NIST standard identifies this constant with. So I found a few discrepancies in the NIST standard, which is one of the reasons why I started doing modified unit analysis, because I found some strange things, which I've talked about before, but I think I can explain it better now than when I presented this before using my new tools that I've developed. And so first I just want to do a quick review of modified unit analysis. Now, the basis of the foundation of modified unit analysis is that when I let the value of 2 pi have the units radians per cycle, in other words, there are 2 pi radians in one cycle, or 2.68 radians in one cycle per cycle. When we let the value of 2 pi have the units radians per cycle, especially in the domain of the cycle. Okay, when we do that, this is modified unit analysis. So I'm modifying unit analysis to insist that we put radians and cycles back into the unit analysis, and this is something that was historically and by convention taken away. Okay, this was taken away from us, and I want to give it back. I want to put it back. And the only way I can do this is to develop my own modified unit analysis, my own standard, which I am starting to warm up to the idea of calling it just the X standard. Okay, but I'll continue to use the term modified unit analysis for now. It's just a little bit hard to say that, modified unit analysis, and so MUA is a little easier to say. So this is the foundation of modified unit analysis. Okay, so modified unit analysis is in the focuses on the cycle, so I am in the domain of the cycle. So in modified unit analysis, I am on a per cycle basis. Okay, I am focusing on the cycle. And so here is an animation that I'm using to show the relationship between the circle and the wave. Okay, this is one cycle around the circle is equal to one wavelength. Okay, so the circumference of this circle, so I am associating the circle with the cycle. I'm coupling the circle to the cycle, and so once around the circle determines the wavelength. Okay, and so this is just a schematic. This is not necessarily what I think waves look like. This could be, the circle though could represent the soliton, John Macken's soliton wave, which is a circular looking wave. And then you have traveling waves that are more sinusoidal. And so the sinusoidal pattern is again a schematic. This isn't necessarily what the waves look like. They might look like this, they might not look like this. I know that water waves kind of look like this, but they are not sinusoidal waves. They are, they can have all kinds of shapes. And so this is just a schematic for the idea of focusing on the cycle. So I want to think in terms of cycle, and so and I'm putting the cycle term back into unit analysis because I want to make sure that we don't forget about the cycle. Okay, so cycles per second. Okay, cycles per second are the units of the of frequency, and meters per cycle are the units of wavelength. Okay, and actually let's just be a little more thorough here. Let me go here. Okay, so cycles per second is frequency, seconds per cycle. So in fact, this is what I really want to focus on. I'm actually going to do something here. I'm going to, let's see, I want to cut this out. And I'm going to remove that, and I'm going to put this here because really I want to look at this is the seconds per cycle, and this is the meters per cycle. So meters per cycle is the wavelength, and seconds per cycle is the amount of time it takes for one cycle. So in this discussion, I want us to really think about the time it takes for a cycle, and the length of the wave that is created in that time period, okay, in that time period. So that is why I want to put that there. And let's just have a quick look at the units again. So it is my opinion that a mistake was made in the past, that where they kind of removed the cycle term, they removed any they basically said that angle is unitless, but angle is a unit. So angle is a unit, cycle is a unit, radian is a unit, but I am going to focus on the domain of the cycle, which is one complete cycle. Okay, I don't care about radian. If you want to switch to radian to do your sine and cosine calculations, that's fine, but I want to focus on the cycle. Okay, so historically, they would write frequency like this. They would write frequency as 1 over s, or s to the minus 1, and they would write the, they would forget to write the 1 when they had a second term. So when they had Planck's constant, when they had the joule times second, okay, when they had the joule times second, as the action constant, then they wouldn't rate that. So I think it's a mistake. I think in the action constant they shouldn't write joules times second. They should write joules times second per 1, because that 1 means one cycle. Okay, cycles are countable. This is the reason they use the number 1, but this is not the numerical value of 1. This is the symbol of 1. So instead of using the 1 symbol for the cycle term in unit analysis, I use this little triangle term. Okay, so that is my quick review of modified unit analysis and the reasoning behind the logic of switching from the NIST standard to modified unit analysis. Okay, so let's have a closer look at some of these constants. Like I said, I found a problem with a couple of the constants, and the constants that I had trouble with in the NIST standard were the constants that play a big role in the own particle model. And so I found this really bothersome. And so here we have Planck's constant in the NIST standard, in the NIST standard. The units for Planck's constant are joule per hertz. Okay, so this is correct. There's nothing wrong with this. Joule per hertz is actually the correct way, least ambiguous, I guess, way of rating Planck's constant, or the units for Planck's constant. Okay, so joule per hertz, joule per hertz are the units of Planck's constant, and hertz in modified unit analysis, frequency is cycles per second. Okay, so this is joule per cycles per second. And then when you rewrite this such that you want to put the second per cycle here, so when you divide by cycle per second, it's the same as multiplying by second per cycle. So you divide by cycle per second, or you can multiply by second per cycle. And so here in modified unit analysis, the units for Planck's constant are joule times second per cycle. And second per cycle are the units of the time period. Okay, so let's just use this little yin-yang here as an example. So one turn is one time period, and that you could say that this is the energy associated with one turn of the own particle model, and or one time period of an oscillating wave, okay, of a wave that is propagating through the medium for the propagation of light. Okay, so this is all related to the medium for the propagation of light, and so this is what I'm seeing. These units literally read the energy of one period of a wave associated with light. So the units in the NIST standard for Planck's constant are technically correct, only I write them a little differently by incorporating the cycle term, which was historically never written. So currently in the standard, they never write the cycle term. I want to expose and explicitly write the cycle term everywhere it is needed to be written. Okay, so I also want to point out that because this has the units of joule of one period, it's the energy of one turn. Okay, this is the energy of one turn of the own particle model, or of a propagating wave. Okay, I would like to give this a name. Okay, and so, but this is not the photon. Okay, so in the mainstream language, the photon is the energy of the equation E equals hf. Okay, so this is not the energy of a photon. This is the energy of something else. And so I need to give this a new name. And so I came up with the name. So this is the energy of one turn, if you want to think of it as one turn of the own particle model. Okay, so that is just an analogy. So the turning of the own particle is exactly what is generating the wave. And so one time period is one wavelength, is one turn, is one cycle, is one oscillation. And this is the energy of one of those turns. And so I came up with a really cute name of photurn. Okay, so H is the energy of one photurn. Okay, one turn of the wheel of Dharma, if you understand what that means in Buddhism. It's a teaching. Dharma is a teaching. So this is one turn, and I'm calling this Planck's constant. I'm going to refer to as the energy of one photurn. Okay? So there's another constant that I use a lot in modified unit analysis, and that is Planck's constant divided by the speed of light. And when you take Planck's constant and divide it by the speed of light, it converts it from an energy constant to a momentum constant. Okay, and so in the main language, momentum, the letter P is often used for momentum. And so I'm just going to do that here just for convenience. I don't like using the letter P for momentum because I use the letter P for power. So coming up with an unambiguous symbolic language for this has been very difficult. I still haven't perfected it yet. And if anyone has any suggestions, I would be happy to hear them. Okay, so when you take Planck's constant, so let's go back to the Planck's constant here. Okay, so Planck's constant has units of joule times the time period, okay? So when you take that and divide it by the speed of light, you're dividing by meters per second, right? Then you end up with the units of momentum. And so the units of Planck's constant divided by the speed of light in modified unit analysis has units of momentum times second per cycle. So this is the momentum of one time period, okay? Or you could say it is the momentum of one photon. Okay, this is the momentum associated with one turn of the Ohm particle model. But here is the problem I have with the NIST standard, with the NIST standard. In the NIST standard, they report the units of H over C, which they report the same value I do. So I get the exact same value they do, but they are, sorry, so 2.102, etc., times 10 to the minus 42, 2.2102 times 10 to the minus 42. Okay, so the values are the same. And so, but the units of, they are using the units of kg for this constant. And so this is a little perplexing because when you look at the units here, okay, so if I throw away the delta term and I cancel the two s terms, I end up with the units of kilogram times meter. But kilogram times meter doesn't really have any physical, physics meaning, any physical meaning, and so anything that's very useful. And so I think because they never allowed the cycle term into the language, I think they kind of got a little confused here. They didn't know what this constant meant. This is a very important constant to me. This is the constant of momentum. Okay, so this applies both to light and to particles, and so this is the photon of momentum. Okay, the momentum of one turn, one oscillation, one wavelength of a light wave. Okay, so I think this is a problem here. So what they did to correct it, and this is something that goes against everything that I understand, physics and math and rigor and all of that combined, okay, what they do is they take the units, so the units are going to be kilogram per meter in the standard model. They don't write the delta term. They cancel these two s's and they end up with kilogram times meter. And so what they do is they take this constant and they multiply it by the unit of inverse meter to get rid of this meter term right here. Okay, they're only doing this to get rid of this term so they can report this constant as having the units of kg, of kilogram. Okay, so this bothers me a lot because this value does not have the units of kilogram in any universe that I understand. And so doing this, and they're doing something that I not only prevent, but I insist we don't do in modified unit analysis. You do not multiply a constant with units. You have constants and you have units, okay? And you do not multiply a constant with a unit just to get, because you want it to come out to units that you understand, okay? So this is one of the reasons why I think we need to fix the NIST standard, at least as it relates to quantum mechanics. This could be why quantum mechanics is so confusing, because they're doing strange things like this. No wonder quantum mechanics is strange when you do strange things like this, okay? And so in modified unit analysis actually corrects this problem, and so you can see you do not want to cancel these s's. If you do, then you are missing the true meaning behind this constant, which is the momentum of one period, one cycle, one rotation, one oscillation, one wavelength of the own particle model, and or the propagating light. Okay, well, these are intimately related. But wait, there's more. Okay, they make the same mistake. They do the same thing. I have the same problem with the constant that is h over c squared. So when you take h over c squared, you get another constant. This constant right here, it's a very small number. It's a very small number, okay? And so in modified unit analysis, when you take h, modified unit analysis, h with units of joule times second per cycle, and you divide it by the speed of light squared, okay, you get the units of kilogram per hertz, which is very similar to the joule, what we did with the joule, okay, so joule per hertz, so this is kilogram per hertz, which is kilogram times second per cycle, which is the mass of one period of the own particle model, okay, one cycle, one rotation, one oscillation, one period, one wavelength of the model, okay? So, and again, this applies both to propagating light and non-propagating light, i.e. the solitons of John Macken's wave model. Okay, so one turn. Now, this is not John Macken's idea. I don't think he agrees with this idea, but I still like to reference his model because I think that the yin-yang symbol is sort of a nice schematic for his model, and that is why I'm using this right now. Okay, so this constant in modified unit analysis interprets as the mass of one wave period of the soliton wave. So each turn of the soliton wave generates a tiny fraction of the mass that we would experience of this particle. Okay, the wave period determines the sensation that we feel as the mass of the particle, and so this is the h over c squared is a very small number. You can think of it as the quantum of mass. Okay, this is the quantum of mass, a cycle of mass. This is the mass of one wave period. Okay, but here is what the NIST standard does. Okay, so in my model, clearly, even if I get rid of the cycle term because the NIST standard doesn't have a cycle term, the units of h over c squared are going to be kilogram times second. Okay, so, but in the NIST standard, they report the h over c squared as having units of kilogram. Now, this is strange because h over c also had the units of kilogram. So how can h over c have the same units as h over c squared? Well, here what they're doing is they're taking the, so you can see that the units of h over c squared are kilogram per hertz. So what they're doing is they're taking h over c squared and multiplying it by the unit hertz, which will cancel this, and then they can report kilogram as the units for this constant. And again, this goes against everything that I believe in terms of mathematical rigor, in terms of rigorous physics. Okay, you should not, cannot, shall not, will not multiply a unit by a constant. You have constants, okay, you have constants, and you have associated units. Units are associated with a constant, not multiplied by a constant, okay? They are multiplying a unit by a constant to get a unit that makes sense to them, because kilograms times second doesn't mean anything to the standard model, okay? So, but if they had put the cycle term back into the units, if they had let, okay, if they had let 2 pi have units radians per cycle, then they definitely wouldn't be making this mistake. Okay, this is a mistake. This is a mistake. Okay, in my opinion, this is a mistake with a capital M. And the three constants of nature that are the most important in the particle model, which is the constant of energy, the cycle of energy, okay, the energy of one turn, one cycle, the photon. Okay, so the energy of the photon, okay, the momentum of the photon, and the mass, effective mass, the mass contribution of the photon are the three most important constants in modified unit analysis, and they are the three least important constants in the NIST standard because they're not even doing them right. Okay, they're not even doing the units right. So they don't have any physical meaning in the standard model. And if they do have physical meaning, they're misinterpreting them because they're getting the units wrong. And that is why I am doing modified unit analysis. And all of my modified unit analysis is sort of centered around this character here. H is the center of the universe, I guess, in the terms of the quantifying the own particle model. Okay, so everything is based on it. So you have H over C, you have H over C squared. Okay, and so that is how I get the constants of nature. And you can do, you can answer real questions, you can solve real problems using these constants if you think of light and even particles, even matter, in terms of the own particle model, okay, which I've talked about a lot in the past. Okay, so I just wanted to get this out quickly. Let's just see here. Here are the constants all on one page if you just want to have something to look at quickly. We've got, the H with units of joule times second per cycle, and then you have H over C, the momentum term, which is momentum times second per cycle, and then you have H over C squared, which has the units of kilogram times second per cycle. And so this interprets as the energy of one wave period. This interprets as the effective momentum, the momentum contribution of one cycle. Okay, so this is momentum of one wave period. And this is the effective mass, when you're dealing with like electrons and protons and soliton particles, this is the effective mass of, with units kilogram per second per cycle, the mass of one wave period. Okay, and so for the soliton model, one period is one turn. Okay, and I'm going to take this and I'm going to copy it. Let me just grab this and put it up here. Okay, this is my photon model. Oops, sorry about that. Come back. Okay, this is my photon model where each of these constants corresponds to the energy, momentum, and or mass of one turn. Okay, so these are all just different ways of looking at the same thing. Okay, energy isn't one thing, and momentum another thing, and mass another thing. In the own particle model, one turn of the own particle model has an energy, has a momentum, and has an inertial mass. Okay, let's just leave it at that. It's got an inertial mass, and so that's why light has momentum. Light has energy and momentum, and particles have energy, momentum, and mass. Okay, so yeah, so I'm going to leave it at that. And in the next video, I want to transition from the domain of energy to the domain of power. That's going to take a little more explaining, and so really here I just wanted to get to the problem with the NIST standard and then leave you with the links so that you can have a look at the NIST standard yourself, and maybe you can find some other problems with it that are similar and or associated. And yeah, so I'm going to leave it at that, and I'm going to have spend the rest of my afternoon relaxing, and I will I guess I'll be back.